everyone. So, as we will continue what we did in the last section, we were doing some stuff on derivatives, and it was all about multivariable calculus. And we have learned how to define a derivative, how to define them in higher dimensional forms from one Euclidean space to another Euclidean space. And we had also defined how to how to make sure the function is continuous at a certain point A, and how to find the derivative of that function at a certain point A. But until now we have only talked about how to calculate derivatives in general and not partial derivatives. So partial derivatives are also a thing, and they are mostly defined by how the variables are shaped. So for example, if we had a function f of x comma y, and we were looking to find the derivative with respect to x, then we would say that the partial derivative of f of x comma y with respect to x is, and we would write this as d1 of f x comma y, where d1 just denotes the derivative with respect to the first variable. Okay, so depending on how the function is shaped or how the function is actually represented, here we can see it's written as f of x comma y, making x as the first variable and y as the second variable. Now these are the things that we will come to know very soon, but before that we would like to solve bunch of more problems in differentiation, and we would like to state a lot of theorems, and we would like to understand in quite deep what this exact things in analysis mean. So apart from calculus, analysis is a much broader term, and it deals with the reasonings of calculus, right? So calculus is just the calculation part, but well, analysis deals with all the logic behind it and also the calculation. So we did a few examples in the last section, but in this one we shall do some more. So let's begin. So let us start with example 1 for today. Example 1 would be so we are going to find the derivative of a function f which goes from r squared to r, and it is defined as f of x comma y equals to a to x plus y, and inside we have g, so we can call it, let's say, g dt. Okay, and g is basically an integrable function which is continuous from r to r, so it's continuous, right? So we need to find the derivative of this function f. Now notice that it is not a very usual problem as regards to the previous problems that we have solved, because this one involves integration, and when we are solving such a problem, we need to keep reminded of that when you are doing an integration but with variable limits. Let's say in this integral the limits are from a to x plus y, where a is a constant surely, but x plus y, it's the variable in touch, right? It's the variable in discussion in the variable f. So in the function f, the variables of importance are x and y, and in the integral they're defined as the limits of some function. So x plus y could be some function h of xy, but they are there, right? So that's how the integral is dependent on the variables. Now how do we find the derivative of it? So it's no different than to find a derivative of a different function composed of x and y. and we can use our same methods to do that. So what we can do is as follows. We can say that h of t is a to tg, integral of a to tg, and we don't really need to understand how the x plus y function works, okay, because h would be the first function and then would come x plus y. So what we can do here is we can write f prime of x comma y as, firstly we are going to find out this h of x plus y's derivative, right? Now due to the chain rule we have df a comma b, so the derivative at the point a comma b would then be equal to dh of a plus b, firstly. So this is how we are going to do it, multiplied by pi 1 plus pi 2 derivative at the point a comma b. So this is basically dh of pi 1 plus pi 2 at a comma b multiplied by pi 1 plus pi 2 whole prime a comma b. Okay, now the derivative of h can be found out from the basics of calculus. So the fundamental theorem of calculus says, the fundamental theorem of integral calculus rather, if you remember, we had done this back in the course where we had done integral calculus. I have defined this kind of functions there and how to do this kind of limits. Such a video would also be included at the end, so that you don't need to don't need to go to a separate video to understand that facts. So you might as well learn it here. The fundamental theorem of integral calculus says that so if we were to differentiate d dt of a to t g, let's say gx dx for example, then this would just give you g of t. This is because we are really here trying to state the facts that g of x is basically inside the integral, which means the answer to this integral a to t g of x dx would be a function whose derivative is gx, right? So gx is continuous and it is integrable. That means there exists some function. So let me write it down clearly. Since it is continuous, it is integrable. So there exists some function p of t in a comma t such that p dash t is gt. Okay, and this would give and this would actually give that since there exists some function, we can write that a to t g of x dx is simply equals to a to t p dash x dx, and this would give you p of t minus p of a. And now differentiating both sides with respect to t, we have a to t g of x dx is p prime t, right? So this is the whole thing we wanted to prove. Now coming back to our problem, we see that df ab is basically, now dhab, as we had pointed out, is g of at, right? So it basically becomes g. So here we had dh of pi 1 plus pi 2, and we understood that h of t is the integral is basically g of t, differentiation derivative. So d of h of pi 1 plus pi 2 ab is basically d of h of a plus b, which is basically g of a plus b, right? So this becomes g of a plus b multiplied by pi 1 prime plus pi 2 prime a comma b. This becomes g of a plus b and 1 comma 0 plus 0 comma 1 a comma b. So g of a plus b times 1 comma 1, which is g of a plus b comma g of a plus b, which is the derivative for f at the point a comma b. So this would sum up the answer. So as you can see, like, this answers are pretty much constructed from the basics, and they also themselves consist of the basics. They do not really concern with themselves a lot of different and complex results, but rather interesting results. Like, we have used the fundamental theorem of integral calculus here. We use the same definitions of linear basis of like pi 1 and pi 2, because there were two variables, so we used pi 1 and pi 2 and stuff like that. So all in all, these questions are more about how you can apply those formulas and rather less about how to memorize them, because these results should come generally to you. It just should be instantaneous to you that what to use in a certain situation depending on what the question asks you. So as you can see, the question asks you here explicitly to differentiate an integral, and the integral has a variable in it, in the limits. It should be directly clear to you that, well, the integral is basically the inverse function of derivative. So if I'm to basically differentiate an integral, it should give back the function, right? Now the question remains, what is the function actually going to come out? Is it the same function? Is it something plus an argument, or the argument is changed, or something like that? So for that we use the fundamental theorem of integral calculus. Anyway, so that would complete this answer. Let us go to the next problem. So that's the problem we are going to solve. It is said that given a function f belonged f from r to r squared to r, defined by f of x comma y from integral of a to xy. Xy means here x dot y, which is the dot product between two vectors, because you see x and y are two-dimensional vectors. And then the definition follows, and then we have to find the derivative of f, and g is basically a real function and it is continuous. So I'll give you 10 seconds to try and think about this problem based on what you have done, whatever we have done in the previous one. So I think that should be enough time. Now, to do this problem, we need to be careful about a certain number of things, like there is the dot product, and the dot product needs to be carefully investigated. Now, how do we investigate the dot product? So if you remember from previous exercises, we can write as follows. So this basically is the composite definition, right? Where t of course is the variable, and pi 1 and pi 2 are your usual linear transforms in two dimensions. And we would like to find out how to find the derivative of this, but this is very much easy using the chain rule. Let us try to do it. So using the chain rule, we have we do have this df at the point a comma b is basically derivative of a to t g at the point a comma b. Basically this is not quite it, because what you want to do is this. Of pi 1 cross pi 2 at the point a comma b multiplied by derivative of pi 1 dot product pi 2 at the point a comma b. So how do you evaluate this? Well, obviously, even evaluating this integral, this particular function, the first part is pretty trivial because of the last problem as well, where I had exactly defined how to find the differentiation of an integral whose integrand is continuous in the interval, and it's also defined at the endpoints. So since it is continuous at all r, so it's defined at all endpoints, obviously. So this would just be g of a dot b, which is a dot product b, multiplied by, now this product's differentiation is basically pi 1 prime pi 2 at the point a comma b plus pi 1 pi 2 prime at the point a comma b. This gives you g of a dot b multiplied by 1 comma 0 b plus a into 0 comma 1. Therefore, this gives you b comma a, and therefore what you can do here is you can write b into g of a dot b comma a into g of a dot b, which is our required answer for that derivative. So you see that these problems are mainly shaped by the fact that you just need to consider two-dimensional or three-dimensional, whatever it is, you just need to consider them, and then you need to have a perfect way to define them as a composition in order to use the chain rule. So the chain rule is the only way you can evaluate this kind of derivatives, or all the derivatives for that fact, and that's the easiest way, of course. So, well, using that we can always find out this kind of derivatives easily, right? Okay, so let's move on to the third problem. Problem 3 is just like follows. So this time we have a function from r cube to r, and it is defined by from xy. It's not xy actually, so let me just rewrite it. From x to the power y to sine of x sine of y sine z g, and that function sine of x of sine of y sine z is a function whose derivative has been found before, right? So we are going to use that as a known derivative because we know that we have already used that before, and that we are going to treat that as a function hx comma y comma z whose derivative is found. So therefore let sine of x sine of y sine z, right? And the part where the derivative is found before, that video would also be included, and you can refer to that video to understand how to find the derivative of this function exactly. Now for this part we can write this as now. If you were to find out a function which goes from a of t to b of t, where a of t and b of t are two different functions and the integral is g, the integrand is g, and this a of t and b of t basically need to be composed with another functions which are like this, right? So how will you plan to do it? Well, one way to do it is, as you can see, the function goes from r cube to r, and then it would be basically a function where you would have three different kind of derivatives. So the matrix of the derivative would be of the from 1 cross 3, right? Because it goes from 3 to 1. Now, since the both of the limits here are basically derivatives, right? Both of the limits here are basically derivatives. So we need to understand that a function from a of t to b of t, g, can be composed, and there should be multiple layers to it, right? So this kind of a definition may not work. What could rather work is something like this. So we only want h of x, y, z's composition, right? So firstly, what you can do is this: you can write an integral where it goes from, let's say, we can do u actually. So let's do that. U to t g, and you compose it, and you basically compose it with, firstly, from u to t, you compose it with h of x comma y comma z, and we are going to treat that t is the variable here, right? And u is also a variable, but what we are going to do is we are going to find out that this variable right here is something that we would like to do. So we are going to define another function as like this, and find out that this would be equal to exactly x to the power y into sine of all that things g. And to do this, we note the following fact, that if h equals to a of t to b of t g, then h prime is basically b prime t into g of bt minus a prime t into g of at. Okay, so this is what we are going to note. So therefore df at abc would just be equal to, now the b prime was basically h of xyz, right? So it's basically dh of abc to g of h of abc minus a prime was x to the power y, so d of x to the power y at the point abc into g of x to the power y. Not actually x to the power y, it should be it should rather be a to the power b, right? Because ultimately you are going to put the value in, so yeah, it's x to the power b. So what we are required to find is the derivative of these two functions, right? And this rule directly follows from fundamental theorem of integral calculus once again, because there exists some p such that p dash equals to g for all let's say x belongs to a of t comma b of t. So that's how we can find out this definition. Okay, now to find out those derivatives, obviously we can use a lot of various different functions, but we're going to use them and prove these derivatives in the next section. And for now, I think this would be a good time to end, and the added video would also give you a very much hint about how to find out this function, although I'm going to do it again in the next video, but still this would be added as an implementation. the derivative of a function f of x at x equals to a is given by f dashed of a equals to limit x tends to a f of x minus f of a whole divided by x minus a. So this is the definition of derivative of a function, and we can use it to our advantage to find the different derivatives. Now let us begin by solving different basic derivatives first, and then we can do the other ones later. So what are the derivatives that we are going to find? So trigonometrical identities are a great way to start off this list of chapters. So trigonometrical identities. Trigonometrical identities are a better way. So the derivatives which we are going to find is sin x and cos x. So let us begin by one of them. So sin x, let f of x equals to sin x, then the derivative of f of x is, so now we try to find the derivative using first principles, and it won't be that much hard because as we have already encountered this kind of problems before, we shall be accustomed by now to as to how to approach this kind of problems and how to solve the particular limit. So here, as you can see, the question asks us for f of x equals to sin of x. So the limiting definition would be limit x tends to a f of x minus f of a by x minus a, right? Another definition for the limit is what I am going to write now, is the definition what we are going to use while solving the problems. This is limit h tends to 0 f of a plus h minus f of a divided by h. This is a more standard definition of derivatives, and I think this is more useful than the other one, because the first one is usually the one where we convert from limit to derivatives, but this one actually helps us to find the derivatives in terms of the functions, elementary functions, directly from the limit. So using the value of f of x, we can write this as like this, right? Now we can use the formula using the formula for compound angles, that is, we can add and subtract angles inside sine, and we can also express them. So we can use the formula sine of a plus b equals to sin b cos a. So this is the formula, right? So using this formula, we can see that sin of a plus h similarly would be now. When this is done, what we can do now is we can find the limit L. Actually here we do not read the answer L, we already have a name for it. So f dash a is equals to limit h tends to 0 sin a cos h plus sin h cos a minus sin a divided by h, right? So what we can do is limit h tends to 0 sin h by h into cos a. So we can just take the second term here and we can take the first term common and we can write limit h tends to 0 1 minus cos of h by h, right? So this limit is 1, so it becomes cos of a, because we have learned about the limit x tends to 0 sin x by x in the previous videos. And the next one, sin a into, now we first use the formula for 1 minus cos theta is equals to 2 sin square 2 by theta. So using that formula it becomes minus 2 sin square h by 2 by h, and this limit goes to 0 because firstly sin h by, if it was sin h by 2 we could have found the answer, but since it is sin square h by 2 it goes to 0. So the answer is cos of a. So the derivative of sin of x at the point a is cos of a, right? Okay, we can do a similar calculation for cos of x as follows. So case 2 is, now the derivative would be defined as follows. Defined as follows. F dash a would be equals to limit x tends to a f of x minus f of a by x minus a, from which we can substitute h equals to x minus a to find the new definition which was more useful to us, which is like f of a plus h minus f of a divided by h, right? Now this would give us limit h tends to 0 cosine of a plus h minus cosine of a whole divided by h, right? So this means now we have to use the formula. Now trigonometry that cos of a plus h is equals to cos a cos h minus sin a sin h. Using this formula what we can do is as follows. Using this we have f dash a equals to limit h tends to 0 cos of a cos of h minus sin of a sin of h minus cos of a divided by h. So we can again distribute it as follows. Take cos of a common and we can write it as limit h tends to 0 cosine of h minus 1 by h minus sin of a common limit h tends to 0 sin of h by h. As we know from the previous example, this limit is 0, so this is 0 minus sine of a into 1, because this limit is 1 as we have done in previous examples. So the answer becomes minus sine of a. Okay, so that's the derivative we were trying to follow. A third example now could include the derivative of e to the power x. Derivative of e to the power x. So let f of x equals to e to the power x. Then let us evaluate the derivative at the point x itself. So what we are going to do is we are going to write it like this: f h tends to 0, f of x plus h minus f of x divided by h. Okay, so this tells us limit h tends to 0 e to the power x plus h, because f of x is e to the power x. So f of x plus h would be e to the power x plus h minus e to the power x whole divided by h. We using the rule for indices, the law of indices, we can write this as e to the power x into e to the power h minus e to the power x whole divided by h. Now we can take e to the power x common, as the limiting variable is h, so e to the power x is basically a constant here. We can write e to the power x into limit h tends to 0 e to the power h minus 1 divided by h. And as we know from previous experience, this limit is again equal to 1, as I have proved. So the answer is e to the power x. And as you can see, the derivative of e to the power x is e to the power x itself, which actually means that we can find the derivatives very clearly here, and this is the only function whose derivative is itself. Now once we are clear with the basic definitions of how to find derivatives, I can give you a list of basic functions and their derivatives. So let me write it down. List of common functions and their derivatives. So now I'm going to write down all the functions and their derivatives, and from the next video onwards we would be trying to implicate them and learn more about the chain rule. Okay, so the more we learn about the chain rule, the better. Okay, so derivative is usually written as d dx, where x is the derivative variable, and in bracket we write the function which we are differentiating. So this is the format that I am also going to use. So these are the three functions. Firstly, d dx of x to the power n is n into x to the power n minus 1. d dx of ln of x is 1 by x. d dx of a to the power x is a to the power x into log of a. Number 4. is a to the power x. Number 5. Number 6. of tan x is basically equals to sec square x. Number 8. d dx of cot x would be equal to minus cosec square x. So I think these are some of the basic things, and there are other things as well that you need to know, but for the time being this should do. this should actually work pretty well. So let me write down some more rules. If fx and gx are two differentiable functions, then ddx of fx plus gx is equals to ddx of fx plus ddx of gx. So basically, if you are given to find out the derivative of the sum of two functions where both of the functions are differentiable, then the answer is basically the derivative of the first function added with the derivative of the second function. Similarly, if you are given something like this, where you have given the multiplication of two functions, then what you can do is try this. And finally, if you are given two functions in the form of division like this, then the answer is simply gx whole squared gx into f dashed x minus fx into g dashed x. And obviously here g of x not equals to 0. So these are the three rules also that you need to follow when solving for derivatives. And along with this, the most important theorem of all is the chain rule, which we shall do in the next lecture, where after that we can be free to evaluate any derivative we want by hand. It's a magical rule, so evaluating derivatives won't be a problem anymore once you learn and once you get a hang of that rule. But before that, you need to be very much confident about all these formulas. You need to memorize them by heart. Let us begin with the chain rule. The chain rule states that the derivative of a composite function where f of x is continuous for all x belongs to u, where g is a function such that it goes from d to u, and g is continuous and differentiable at x belongs to d, then the derivative of the function f of g of x is given by f dashed of gx multiplied by the derivative of gx. So it might look that it's not such a big result, and okay, the definition might be a bit more complex, but the result itself says that the ddx of f of gx, considering all the other technicalities solved, that f is continuous at g of x and f is differentiable at g of x and g is differentiable, we can say that the function f of gx can be differentiated by just differentiating the function f at the point g of x and then just differentiating g of x at the point x and multiplying them together, right? But this simple definition is the key to solving all of derivatives problems. As you can see now, So if you remember the basic derivatives, which I can recall one by one, it's like x to the power n is n into x to the power n minus 1, sin x is cos x is minus sin x and stuff. Then logarithm of x is 1 by x, e to the power x is e to the power x itself. Now we can try and find out the derivative of. So we are going to do a bunch of problems now. So let us do ddx of e to the power ax. So ddx of e to the power ax. So first recall the basic function. The function, what it starts with? It starts with the function e, right? E to the power something. Now, what is the most basic representation? It's e to the power x. So if you remember, ddx of e to the power x was e to the power x, right? So we are going to copy this and write the answer itself. That is, the answer should be whatever is given. So e to the power ax, right? So pretend as if this function was e to the power x only and write the whole function down. But then multiply it with, go to the next level of the function where the anomaly is present. So it should have been e to the power x, but it isn't, right? What is there instead of x? It's a of x. So now it should be ddx of ax, where a is just a constant, and when you do a constant x, a times x, the ddx of x is just 1 and constant just comes out. So the answer becomes a into e to the power ax. This is because ddx of x is just 1, and also ddx of a constant c times any function f of x is just c times the derivative of the function. So the constant just remains multiplied throughout. Okay, next example. Because the more examples we do, the more it would be easier for you to understand. ddx of ln of, let's say, x squared. So how do we do this? Well, first we try to think what the ddx of ln of x is, because the first function is ln of x, right? So ddx of ln of x is equals to 1 by x, right? So pretend as if this function is ln of x and we write the derivative as 1 by x square. So do not directly write 1 by x because you just need to pretend. But when you are going to write the derivative, you are going to write the same thing, and instead of x, whatever is present, you are going to use that. But you are just pretending it is x, right? Now you multiply and you do the derivative of the next level, the expression which is present instead of x. So x square is present here, so we do x square. So it's 1 by x square into ddx of x square by the rule for differentiation of powers is 2 into x to the power 2 minus 1, right? So it will become 1 by x square into 2x, which will give you 2 by x, right? Okay, one more. Let us try to evaluate ddx of log of sin x. Now, how many layers are there? Let me just clarify this like this. Layer 1 is the first layer of function. This is log. So layer 1 is log x. And what is layer 2? Layer 2 is sin x, correct? So it is log x and it is sin x. Now, the answer can be written directly if we have that in mind, because we differentiate one by one and we keep on doing that until we reach the inner bottom where x is present. So ddx of log of sin x is simply equal to, firstly we do the ddx of log x, which is 1 by sin x, and then we do the differentiation of sin x, which is cos x, right? And cos x by sin x is simply cot x. So you see, we have got the answer. ddx of log sin x is just cot x. Okay. So this is not really a very hard one to be done. Let us move to other examples. we need to find the derivative of this function. So here comes the harder ones, or rather you can say the more complex ones, because if you know what to do, I do not think this would be at all hard for you any more than it was the last problem was. But then again, this would be a bit more calculative, right? So we first need to understand the layers and stuff. So what is layer number 1? Layer number 1 is of course sine of x, right? Sine and some x inside it, which we are going to pretend is x. Layer 2 is of the form fx by gx, right? Layer 2 is of the form fx by gx, which we learned before that the derivative of two functions can be evaluated how. I'll just write it down here, that ddx of fx by g of x can be evaluated as fx into g prime x, right? What is layer number 3? So in fx there are two layers, right? In fx there are two layers. How many layers are there? Fx has a layer which says that the inside function is x square plus 2. Similarly, gx has a layer which says that the inside function is e to the power 5x plus e to the power x, right? But these layers do not really matter because we already have a fx by gx thing here, right? So we are going to use them here directly. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.